going to continue our study of this paper, Spacetime Algebra as a Powerful Tool for Electromagnetism. And this is intended to be part of a general introduction to geometric algebra as best I can. But I really do want to focus on the spacetime algebra because that's what's most applicable to at least elementary physics. And we have made huge progress. We have gotten all the way through 3.4, and now we are going to start on section 3.5, the pseudoscalar, Hodge duality, and complex structure. So let's begin. The expansion, equation 3.7, of a multivector in terms of elements of differing grade is similar to the expansion of a complex number into its real imaginary parts, as we emphasized in section 3.3. So as a reminder, this is the expansion 3.7. A multivector has a scalar part, a vector part, a bivector part, a trivector part, and a pseudoscalar part. And already the pseudoscalar part has been broken down into a real number times I, where we have defined I to be gamma 0, 1, 2, 3, which we can immediately translate to gamma 0 wedge, gamma 1 wedge, gamma 2 wedge, gamma 3, because it's orthogonal. These vectors are all orthogonal, and all of the lower grades vanish, but the highest grade remains. And so this, so now you see this. Every one of these others, you'll notice, is just given its own symbol, but this last one is a real number times I, because there's only one dimension in the pseudovector space. This is all important for what we're going to talk about today. So I always represents this thing, this quad vector, and it always gets slapped on at the back as the pseudo vector. It turns out we're going to do this a couple more times. This simplification you're going to see a few more times. And in fact, as a little bit of foreshadowing while we're here, we could rewrite this as, let's see, how could we rewrite this? Hold on. We could rewrite this by making this alpha plus beta I, taking the pseudoscalar, the one-dimensional pseudoscalar, and the one-dimensional real number, putting them together, and then adding the vector, bivector, and trivector. And then this kind of looks like a complex number, right? And that's the idea that we're pursuing now in this section, is this naturally has the feeling of a complex number, especially when we remember that I squared equaled -1 in our particular algebra, our spacetime algebra. Okay, so that's a little bit of foreshadowing. So then they write, in fact, this similarity, that is the similarity of real and imaginary parts, is more than an analogy because the pseudoscalar I also satisfies I squared equals -1, which makes the subalgebra of the form, is that a zeta or a chi? That's zeta, right? Zeta equals alpha plus bi. My apologies if I misnamed that Greek letter. For some reason, I'm blanking on it. But a subalgebra of the form alpha plus beta I, completely equivalent in practice to the complex scalar numbers. However, hence, we do not need to additionally complexify the algebra in order to reap the benefits of complex analysis. The complex algebraic structure automatically appears within the spacetime algebra itself. So that just means we have access to complex numbers inside the spacetime algebra. If we think of alpha, the scalar and the pseudoscalar part, the sum of them, where with this addition is, of course, the same kind of addition I talked about in my lesson on vector addition here. But if we freely think of this as a complex number, this will behave and produce all the results of complex analysis. Now, one thing to be a little bit careful of is this notion of I squared. Now, as a review, right, I squared is literally the space-time product of I with itself, right? And you have to be very facile using this rule that for basis vectors that are orthogonal, they anti-commute, right? So you can switch A and B as long as you introduce a minus sign. So if you write this, and the fact that the spacetime product itself is associative, these two facts together allow you to start moving these things around and shuffling these things around until everything is next to each other, and you end up with gamma 0, gamma 1, gamma 2, gamma 3, each of them squared. And when you rearrange them so that each of these is squared, it turns out these minus signs end up landing on no minus sign at all, and you just take this product. Now, normally, if this was Euclidean space, right, that would be 1 times 1 times 1 times 1, because in Euclidean space, gamma mu dot gamma nu equals delta mu nu, right? And so the space-time contraction of these basis vectors is this delta function, and it would always be 1. But for the space-time algebra, where we have the Minkowski contraction, we get eta mu nu, which induces a minus 1 right here for the gamma 0 squared part, right? So we get, this becomes a minus 1 for this guy. So this ends up being minus 1. Normally, if you were doing a geometric algebra that was just 4-dimensional Euclidean, I squared would not equal minus 1, right? I squared would just equal 1. So it is not true that for every geometric algebra, this pseudoscalar squared squares to minus 1. That's not always true. And in fact, it's not true for regular 4-dimensional geometric algebra. It's entirely this Minkowski metric that I don't know if it saves the day or ruins the day, but it forces this pseudoscalar to actually square to minus 1. So that's kind of an interesting point to take. What matters is the total number of basis vectors you have, which depends on, in our case, we're using M13, but it depends on the underlying vector space that establishes your grade 1 section, right? This vector space, whatever the dimensionality of that vector space is, that's the number of basis vectors you're going to be playing with. And that number of basis vectors determines how many flips you need and whether this final sign will end up positive or negative. So if everything's Euclidean, it really depends on the dimensionality of your fundamental vector space. But if everything's not Euclidean, it depends on the dimensionality of the fundamental vector space and the nature of the metric, right? So just keep that in mind. It's not always true that the pseudoscalar squared is minus 1 for every geometric algebra out there. Okay, to go on, the pseudoscalar I has an intrinsic geometric significance that goes well beyond the theory of scalar complex numbers, however, and has several additional interesting and useful properties. It commutes with the elements of even grade, which are scalars, pseudoscalars, and bivectors, but it anti-commutes with elements of odd grade, vectors and trivectors. All right, let's check that out. Let's study how a basis vector gamma mu space-time multiplies the pseudoscalar, right? So gamma mu times gamma 0, gamma 1, gamma 2, gamma 3, where this is our pseudoscalar in nice space-time product form, where we can go ahead and start commuting these things. So I want to move gamma mu to this side. I want to move gamma mu from the front to the back. So if I did that, if I was able to do that, that would be I gamma mu, and that would be the commutation, I guess, of the beginning. So the question really is this equal, right? Is that an equal sign, or is there going to be some sort of sign difference between the two? Well, I can take gamma mu and pass it through gamma 0, and I'll get a sign change if mu does not equal 0. But if mu does equal 0, then I'll get a sign change. Because if mu doesn't equal 0, you don't even have to commute. You just start commuting the gamma 0 over. So then I can commute it past 1. And again, I will get a sign change if mu does not equal 1. Then I can pass it through gamma 2, and I'll get a sign change as long as mu does not equal 2. And then I finally pass it through gamma 3, and I'll get a sign change if mu does not equal 3. But here's the deal. Mu has to equal one of these 4, right? But if it equals one of these 4, it's going to pick up one sign change. But for the other instances, no, I'm sorry. If it equals one of those 4, it will not pick up a sign change when it passes by that particular indexed basis vector. But it'll only pick up a sign once in this whole process. It'll only not pick up a sign once in this process, right? And every other time it'll pick up a sign. So it has to make 1, 2, 3, 4 flips, one of which will not pick up a sign. So it will make 3 sign changes, of which ultimately that means it's an odd number of sign changes, which means we are left with a sign change. Phew. So that's a long way of saying that the pseudoscalar anti-commutes with each of the basis vectors. And if it anti-commutes with each of the basis vectors, you can do your own analysis and see that it will also anti-commute with a general vector A, expressed in the reference basis. And this is all true for the reciprocal basis as well. So this demonstrates that it anti-commutes with vectors. Now, likewise, trivectors are going to have the same issue, right? With trivectors, you would have something like this, right? You would have 3 basis vectors up front as each part of your trivector basis, and beta will go to the back and get a sign change. Gamma will go to the back, pick up a sign change, which will cancel the sign change that the gamma beta got, but then gamma mu is waiting out there to go and pick the sign change back up. So clearly, I will anti-commute with trivectors as well. However, it will not with scalars. Scalars don't matter at all, and it clearly commutes with itself, right? I equals II, that's an easy one. So we've accounted for every case. We've accounted for, what about bivectors? Well, bivectors would be without this, right? So beta goes through, picks up a negative sign, but then nu goes through and gets rid of that minus sign. So it commutes with bivectors. So that's the explanation of those different commutation rules. So when they say it commutes with elements of even grade, which are the scalars and the bivectors and the pseudoscalar, but it anti-commutes with the vectors and trivectors. All right, we showed that. More surprisingly, a right product with I is a duality transformation from grade K to its orthogonal complement of grade 4 minus K. So let's focus here on this really important concept. Is I is a duality, let's just go with transformation from grade K to its orthogonal complement of grade 4 minus K. Let's see exactly how that works. All right, we start with a grade 0 object, which we'll call the real number alpha. And then I'm going to take that real number alpha and I'm going to right multiply by the pseudoscalar. So I'm going to get alpha times I, which equals alpha times this spacetime product of all the basis vectors. Spacetime product of all the basis vectors, which, because of the orthogonality of the basis vectors, equals this quad vector. So I've taken something from grade 0 and multiplying by I now have something in grade 4, right? So this multiplying by I on the right has converted something from grade 0 to grade 4. All right, let's do it for vectors. All right, we start with an object V, and now I'm going to multiply V by I. And V is, let's do this in full formality. I'll do V alpha, gamma alpha, and then I have gamma 0, gamma 1, gamma 2, gamma 3, right? So this would, let's go ahead and just blow it all the way up. So if we blow this thing completely up, I don't usually blow up these Einstein sums, but why not? So V alpha gamma alpha is V0 gamma 0 plus V1 gamma 1 plus V2 gamma 2 plus V3 gamma 3, and then this is I right here. So by linearity, we now are dealing with these 4 products with I. So the first one is really easy. It's just gamma 0, gamma 0, gamma 1, gamma 2, gamma 3, which is gamma 0 squared. But gamma 0 squared is just 1. So this is going to be just V0, gamma 1, gamma 2, gamma 3. And then the second term is going to be v1 gamma 1, gamma 0, gamma 1, gamma 2, gamma 3. So in order to simplify that, I need to move this gamma 1 from the left of the gamma 0 to the right so I can combine it with this gamma 1 that's already there and get a gamma 1 squared. So if I make that switch, I introduce a minus sign, but then I'm left with gamma 1 squared, right? And gamma 1 squared is minus 1 in the convention that we are committed to. So that minus sign with the swap cancels with the minus sign of gamma 1 squared, and you're left with v1, gamma 0, gamma 2, gamma 3. If you do the calculation for gamma 2, you'll see you have one swap, two swaps, so the minus sign goes away, but then gamma 2 squared introduces a minus sign. So you have v2, gamma 0, gamma 1, gamma 3. And then v3 goes through one swap, two minus sign, one swap, minus sign, two swaps, no minus sign, three swaps, minus sign. So now you have a minus sign for the three swaps, but gamma 3 squared is a negative 1, so you lose the minus sign. So you have v3, gamma 0, gamma 1, gamma 2. And so this final object is in the trivector basis. So this final object is a trivector. So a vector times space-time product with the pseudoscalar gives you a trivector, right? And that's the point, that is the point that we were trying to drive home earlier, that a vector times I, so this is times I guess I should say that in red, right? So a vector, a scalar times I gives you a pseudoscalar, a vector times I gives you a pseudo vector, right? You move from one subspace to another. And if you did this process for a bivector, what you would discover is that the bivector would simply, meaning, well, I guess we should do it. First, I write the bivector in this form using our compressed, semi-compressed notation. I guess the fully compressed notation would go like that. But we're going to use the semi-compressed notation because I want to demonstrate these space-time products, right? So we write it this way, and then I'm going to multiply by I. So I'm going to multiply by gamma 0, gamma 1, gamma 2, gamma 3. Now, I could blow up all, just like I did before, I could blow up all 6 of these guys, right? But I'm not. I'm going to just exemplify it with, say, F1, 2, gamma 1, gamma 2. And you'll see how this, you can generalize this to all the others. And it's gamma 0, gamma 1, gamma 2, gamma 3. So the goal is to demonstrate what do we get when we do this product, right? Well, I'm going to take gamma 2, I'm going to move it over, I'm going to move it over here, which gives me a sign change. Then I'm going to move it over here, which gives me another sign change, which cancels the sign change. And then I have gamma 2 squared, which leaves a sign change. And so that would take me to F1, 2, gamma 1, gamma 0, gamma 1, gamma 3 with a sign change, right? Sign change, no sign change. Well, sign change, undo the sign change, left with a gamma 2 squared, which is a sign change. So that's what this sign change, right here is. And then, once I've done that, then what's left? Well, gamma 1 moves over 1, which introduces a sign change. And then gamma 1 squared is another sign change. So we get no sign change, right? One sign change, and gamma 1 squared is another sign change, so there's no sign change. So I get at minus F1, 2, gamma 0, gamma 3, which is really minus F1, 2, gamma 0, wedge, gamma 3, and that is a bivector. So the bivectors times I go back into the bivectors, right? Phew. So this process we are going to call a process of, I guess I could, now I'm not going to do 3 and 4, right? 4 is really easy. Well, I'll do 4, right? You take a pseudoscalar, beta I, right? And you multiply it by I, and you get minus beta, right? Because I squared is famously minus 1 in this particular, in the space-time algebra. So objects of grade 4 obviously go back into objects of grade 0. Likewise, you'll see objects of grade 3 go back into objects of grade 1. So this process is a duality process. That means I can take any object that's grade 0 and I can find its dual in grade 4. Likewise, any vector has a dual vector in grade 3, where the duality is related to this multiplication by the pseudoscalar I. Now, and 2 is self-dual, right? There are vectors in 2 that are dual to other vectors in of grade 2, right? So that's what we're kind of getting at. Now, the other word that they used here that was important was orthogonal complement, right? And if you look at what we've done here, in this case, for example, we were curious about F12 of gamma 1, gamma 0, right? Gamma 1's gamma 0, that's a little blade out there, right? That's a little blade that it's F12 gamma 1 wedge gamma 0, some little bladey object. And no, F12, I'm sorry, not gamma 1, gamma 0, gamma 1, gamma 2, right? Gamma 1, gamma 2. But the result is gamma 0, gamma 3. Notice that neither gamma 1 nor gamma 2 appear in this blade, right? So this blade here is actually orthogonal to this blade in the sense that it's not composed of any of the same basis vectors. So, which would be different if if we had started with, in contrast, this was F13, which is gamma 1 wedge gamma 3. This gamma 1 is shared with this gamma 1, right? So they do have a basis vector in common. So that's what they mean by orthogonal complement. And this was also true when we did the vector, right? When we looked at the vector, we started with, say, V0 gamma 0, but when we did that calculation, we ended up with the trivector that had 1, 2, and 3 in it and no 0. And of course that makes sense because we squared out the 0 because gamma 0 scalar, gamma 0 spacetime product with gamma 0 is going to be is 1, right? Likewise, gamma 1 spacetime product gamma 1 was negative 1, and it had no inflation part because of the orthogonality. So the only part that existed was the contraction part, and that's the Minkowski contraction, which turned it into a real number. So each of these components of the vector v returned through this duality transformation by multiplying by I an orthogonal trivector, right? An orthogonal trivector. So now normally in three-dimensional space, if you had a vector, everything in the space orthogonal to the vector would live in a plane. But in four-dimensional space, these orthogonalities are volumes, right? Are volumes, which is kind of fun. And this is also true. So this is how it always works, right? This Hodge duality process of multiplying on the right by I, by the pseudoscalar, produces an orthogonal vector that lives in the complementary or the dual subspace. So if you start with the grade k, the dual is grade 4 minus k. So if I started in grade 3, the dual is 4 minus 3, which is a vector. So the dual of a trivector is a vector. The dual of a bivector is another bivector. The dual of a scalar is a pseudoscalar. So that is how all of this language here works, right? The grade 4 minus k part, that's what this, I just went through that. And they say a right product with I is a duality transformation from grade k to its orthogonal complement. So this notion of this duality, this word duality, it's trying to say that there's something about vectors and trivectors, which the duality means these guys, each one of these has an associated buddy in this dual space. And there's a strong relationship between them. And we're going to take advantage of that relationship in the rest of this paper. So just reading on, maybe a little redundantly, we see the unique oriented orthogonal trivector, which is given by gamma 0 I. This is the dual. You read this as the dual of the vector gamma 0. And you know, because you're right multiplying by I, that's the definition of the duality transformation, a right product with I. So I can read this as the dual of the vector gamma 0. And then they kind of work it out, right? They put, here's gamma 0 and here's I, and they know that this is going to go away to be 1. What's left behind is gamma 1, 2, 3. So that's really easy to show, right? Then they also do this again. The dual of the vector gamma 1, 2, 3, right? The dual of that is minus gamma 0. And the way they show this is that they already know that 1, 2, 3 is the dual of gamma 0 I. So they just make that substitution, gamma 0 I, and then you have I times I, because everything's associated. These are space-time products, so everything's associative. So I and I squared in our space-time algebra is negative 1, so you get that negative there, and you have minus gamma 0. Now take note of this, right? They make it pretty clear. The dual of a trivector is its unique normal vector, and here's an example. The dual of gamma 1, 2, 3 is minus gamma 0, all right? Remember that particular one, because I'm going to illustrate a confusion in a moment. The duality is illustrated for the entire graded basis in figure 4. So let's look at figure 4. So here is figure 4. Hodge duality is illustrated using the same basis as figure 2. Well, that's these basis vectors as described here. In other words, it's gamma 2, 3, 0 instead of gamma 0, 2, 3, as I would have done, 1, 2. Although that is the same basis vector, isn't it? 0, 2, 3, 0 and 0 and 0, 2, 3 are in fact the same because you flip 0 twice, so the sign doesn't change. However, 1, 0, 3, I would have done 0, 1, 3, so that would have been 2 flips and then another flip. So that would have been the opposite. So I would have had the opposite in my system, right? In my system, it would have been gamma 0, 1, 3. But I've already spoken about that. It's not, when I say my system, it's this thing I would have I have yet to figure out exactly why they've chosen these basis vectors. There is a reason, and we're going to find the reason. But now's not the time to worry about it because this is a perfectly fine basis. So, but what this picture must be saying is that if you take the segment of the algebra spanned by these basis vectors, the solid basis vectors, right? The basis vector surrounded in solid, and you take its Hodge dual, you will land in the subspace spanned by these basis vectors, right? And what's interesting about this is when I looked at it, I was assuming somehow that the dual of each of these basis vectors, right? If you executed the Hodge dual and multiplied each one by I, you would end up exactly with each of the basis vectors described on the right-hand side. So the dual of gamma 0 we know is gamma 1, 2, 3. We just did that calculation. The dual of gamma 1, which I calculated over here, gamma 1, the dual of gamma 1, and notice I'm using that language because you see the I on the right, you see a multivector on the left, so I can call this the dual of this multivector. Whenever you see that I, that you can just start saying that. And I did this calculation, and I came up with gamma 0, 2, 3, which is gamma 2, 3, 0. Those two are the same by exchange, right? You just move the 0 over 2 spots, right? And 2 spots cancel. Two shifts cancel. So you do get gamma 1 going to gamma 2, 3, 0. Then I did gamma 2. I checked gamma 2, and gamma 2 came out. The dual of gamma 2 was minus gamma 1, 0, 1, 3, which if you move the 0 over twice, you get 1, 3, 0. Then you move the 1 over once, and you end up with 1 ultimate with an odd number of swaps and a minus sign, which makes it 3, 1, 0. And so this one matches with that one. And then I did gamma 3, so the dual of gamma 3 is gamma 0, 1, 2, which is the same as gamma 1, 2, 0. So it is true that these guys do land, those basis vectors do land straight on the basis. The duals of the basis vectors are, in fact, the basis trivectors in this system. So now, what about the bivectors, right? What about what happens with the dual of gamma 1, 0, right? Let's look at gamma 1, 0. Well, gamma 1, 0, the dual of gamma 1, 0 is, according to my calculation, minus gamma 2, 3. Minus gamma 2, 3. Not gamma 2, 3, but minus gamma 2, 3. So this dual goes to here, oops, but there's a minus sign introduced. Gamma 2, 0 likewise gives you minus gamma 3, 1, and gamma 3, 0 gives you minus gamma 1, 2. So this goes here with a minus sign, and this goes here with a minus sign. And what about the dual of the pseudovector, right? Well, the pseudovector, the dual of the pseudovector is obviously the number minus 1. So the dual of a pseudovector actually goes here with a minus sign. So it's not true that every basis vector on the right side is the dual of every basis vector on the left side. I found that, I was surprised. I thought for sure that was the way this was going to be organized, but it probably can't be organized that way, because if you think about how this whole process works, the duality is not an involution. So you couldn't get back from this side to this side with, in other words, the dual of these guys, if you calculated them, would not necessarily come back to its pre-dual, I suppose is the right way of saying it. And in fact, I did that calculation too. So let me erase this. And let's look at these other duals, right? We did this one. We did the dual of gamma 0, 1, 2, 3. And we know that comes back with a sign of minus 1. So we've already done that one. But what about these other guys, right? Well, we've done some of them already. The dual of the trivector 1, 2, 3, well, that's really easy because we know that the trivector 1, 2, 3 is the dual of gamma 0, so that times I, so you get minus gamma 0. And by the way, that's going to be true for all of the basis vectors, the trivector space basis vectors. They're all going to come back to the opposite of the basis of the vector space. And likewise, if you look at the duals of the purely spatial bivectors, and by purely spatial, I always mean there's no gamma 0, right? Gamma 0 is the time-like bivector, or the time-like vector. So all of these are planes in absolute space, right? So this is the dual of the bivector 2, 3. Well, 2, 3 is minus the dual of 1, 0, so the i's cancel out, and you actually get back 1, 0 itself. So the dual of the bivector 2, 3 is actually the bivector 1, 0. Likewise for 3, 1, and 3, 2. So I can actually write, right, that 2, 3 goes to 1, 0, 3, 1 goes to 2, 0, and 1, 2 goes to 3, 0. That's all straight up. But these guys, the trivector basis vectors, they go to their opposites. There's a minus sign appears there. Gamma 2, 3, 0, if you do its calculation, ends up with a minus gamma 1. Gamma 3, 1, 0 is a minus gamma 2. Gamma 1, 2, 0 is a minus gamma 3 on duality transformation by I. And I did those calculations here, right? And they're all written down right here. So gamma 1, 2, 3 is gamma 0 I times I, which is minus gamma 0. Gamma 2, 3, 0 oh, I think I'm missing an I there, right? There should be another I here. Gamma 230 is the dual of gamma 230, right? And I'm just reading it this way. This is gamma 230, right multiplication by I. That's the dual of gamma 230. So the dual of gamma 230 is is the dual of gamma 1 times I, which is the dual of gamma 1, right? But the dual of the dual is minus gamma 1 in this case. The dual of 310 is minus gamma 2. The dual of 120 is minus gamma 3. So these guys come in, their dual has a minus sign over here. So it's not true that the dual of every basis vector in both of the sides of the house here comes back, is another basis vector. It's this minus sign might sometimes appear. We've already seen, of course, that the dual of the quad vector itself, the dual of the pseudoscalar itself, comes back with a minus sign, for example. So I was expecting these things to match up perfectly, but they can't, right? They can't. And I'm sure that the reason they can't is is traceable to the fact that duality is not an involution, which means, multivector M times I, the dual of multivector M, the dual of multivector M does not necessarily equal M. Sometimes it will, but it doesn't necessarily equal M. So that was something that I had to pull from this picture. The part that I don't understand is this use of the introduction of this negative sign here, right? So he introduces this negative sign. That's not a duality transformation. That's literally the opposite, the negative 1 times a duality transformation. So if I do a right multiplication by that thing, I end up with the opposite of the Hodge dual of something. So I'm not sure why they put that in there, but what kind of worries me is when I read the text of figure 4, right? It says, right multiplication by the pseudoscalar converts an algebraic element to its dual. Now first, understand that an algebraic element is a general algebraic element. That's an arbitrary multivector M. So don't let me lead you to think that duality transformations must be from the space spanned by these vectors into the space spanned by those vectors. It almost makes it look as though that's the case. This figure does, but that's not true. Because I could take any multivector, and I could even have this multivector, gamma 0 plus gamma 3, 1. Right? That clearly is a multivector that has a vector part in this space and a bivector part in this space. So this multivector is in both of those spaces. But that multivector has a dual, and that dual is mi, right? And that dual is going to clearly be, it's going to be gamma 1, 2, 3 plus gamma 3, 1 goes to, what did I figure out? I figured out that gamma 3, 1 goes to gamma 2, 0, right? Plus gamma 2, 0. So that's the dual of the multivector M. That's the dual of it. So every algebraic element has a dual, and that dual is the orthogonal complement in the geometric sense, right? So gamma 0 is this vector. What's the entire space complementary to gamma 0 is going to be spanned by gamma 1, 2, 3. Any other vector here any other vector in the entire space is going to be inside. Well, let's see. How do I say this? The largest part of the piece that's complementary to gamma 0 is this 3D volume element gamma 1, 2, 3. Likewise, gamma 3, 1, it's missing the gamma 2, 0 parts, right? So it's orthogonal complement in the geometric sense. And then they give you this example. For example, the dual of a trivector gamma 1, 2, 3 is its unique normal vector gamma 1, 2, 3 minus I, which is gamma 0. Okay, so what gives with that minus sign? I see it here, and I still don't understand it, But that's not the way we defined a dual. We defined a dual by right multiplication by the pseudoscalar I, not the pseudoscalar minus I. And so now they have the dual of a trivector is its unique normal vector gamma 0. But that exactly contradicts what they wrote down here, right? Right down here, and I'll erase my own writing so you can see it. They made it really clear that the dual of gamma 1, 2, 3, which is the right multiplication by I, is minus gamma 0, which is what I would have calculated. So I'm not going to pretend to understand exactly what they're getting at here. Dual elements have opposite signatures indicated here by a flip in color coding. So we'll talk about signatures in a moment. But I just want to point out that this figure 4, it's a little bit awkward to my taste because I don't fully understand the introduction of this minus sign, and I don't like the fact that this here contradicts what's in the text, and I haven't found a satisfactory way through all of this. So we are going to stick with the notion that the dual is always right multiplication by I, and the part that my expectation that these guys had to literally be the dual of these guys, that's just not true. It's the space spanned by these guys is totally dual to the space spanned by these guys. And then on top of that, the implication that the duality transformation only goes from the space spanned by these guys to the space spanned by these basis vectors. That's sort of implied by this diagram, but it isn't true, and I've just given you an example. Any multivector has a dual, and that dual is right multiplication by I. So that means we've covered the pseudoscalar I, right? And we've covered Hodge duality, and the next step is complex structure. Oh, no, I want to cover this. Dual elements have opposite signatures. Let's have a look at that. Okay, so we begin with our favorite one here, the one that we've been scratching our heads about. The dual of gamma 0 is gamma 1, 2, 3, and you can see here is gamma 0, gamma 1, 2, 3. This one's particularly well suited because, or particularly easy, because we just have gamma 0 squared, which through associativity we combine to gamma 0 squared, which equals 1 because it's the space, it's the time-like part. So we know right away that this equals gamma 1, 2, 3. So now, what is the signature of gamma 0? So let's remember how these things are defined. So we have these three formulas to work with, and this will give us a little practice to remind ourselves about reversion, the reversion square and the straight up square, right? So let's calculate the signature for gamma 0, right? Well, that's not hard. We're going to first take the gamma 0 reversion times gamma 0 divided by the magnitude of gamma 0 squared, which is the absolute value of gamma 0 reversion gamma 0. Well, the top, the gamma 0's a vector is its own reversion, right? So we get to review that fact. So this is just gamma 0 squared on top, and this is the absolute value of gamma 0 squared on the bottom, which is 1 over 1, which equals 1. So the signature of gamma 0 is 1. So what about the signature of gamma 1, 2, 3? Well, it's going to be gamma 1, 2, 3 reversion times gamma 1, 2, 3 divided by the magnitude of gamma 1, 2, 3 reversion, gamma 1, 2, 3. Well, gamma 1, 2, 3 does have a reversion. It's going to be gamma 3, 2, 1 times gamma 1, 2, 3, right, over the magnitude of gamma 3, 2, 1, gamma 1, 2, 3, right? Gamma 3, 2, 1, this is beautiful, right? Because it's obviously, we expand that into gamma 3, gamma 2, gamma 1, gamma 1, gamma 2, gamma 3, and then we just start squaring things. That squares to minus 1, then this squares to another minus 1, and then this last one squares to minus 1. That's 3 minus 1s, so that upper product equals minus 1. The lower product's the same thing, but it's squeezed in these absolute value signs, so the lower product is 1, so the signature So the signature of gamma 1, 2, 3 is equal to -1. And the statement was that the signatures of the duals are opposite. Well, that has a signature of -1, this guy. I'm sorry, that is a signature of +1, that is a signature of -1. So on this chart, the way you see it is on the chart, you see gamma is blue, I guess blue is +1, and gamma 1, 2, 3 is red for -1. And this applies, that same methodology applies for all of them, and none of them are any more or less interesting. They're all pretty straightforward. As soon as you take the reversion, you don't have to worry about, shifting things left or right, and how many shifts do you have, and that all goes away with reversion. That's why reversion is so convenient. So dual elements have opposite signatures is a general principle that they're offering, and we just did an example of that. Okay, so let's read on. This duality is illustrated for the entire graded basis in Figure 4. I spent a lot of time talking about that. We will see in Section 5.2 that this duality is for the entire graded base. We will see in Section 5.2 that this duality is intimately connected with field exchange dual symmetry of the electromagnetic field. So 5.2 seems awfully far away at the rate we're going, but we'll get there. So this duality transformation induced by I is equivalent to the Hodge star transformation in differential forms, though it is arguably simpler to work with. I do agree with that. It is definitely it is not even arguable to me. I think it's clearly simpler to work with. But it is equivalent to the Hodge duality. I'm not going to review Hodge duality, but we did talk about it quite a bit in the previous QED prerequisite lectures when we talked about the electromagnetic field using differential forms. But it splits the spacetime algebra into two halves that are geometric complements of each other. That's the two halves we saw above. But don't think that you can't be a multivector that dips into both halves. Now, exploiting this duality, we can write any multivector M in an intrinsically complex form. Okay, so this is a good place to stop. We will talk about complex structure, right? We'll talk about complex structure in our next lesson, right? The next lesson we'll talk about complex structure. Okay, so we've made some pretty good progress, and I'll see you next time.